Hey guys, welcome back. So in this video, we are going to be starting a new chapter which is about current electricity. So till now, all that we learned were about static charges. The charges were stationary. They never moved. We considered one positive charge here, one negative charge here. They are discrete and stationary. But now we are going to be talking about motion of charges, which gives rise to the word current. Current means motion of charges. So in this chapter, we'll see about the behavior of charges in motion and their applications and how they can be made use of. So in this video, we'll be talking about three topics. First one is current density, is just a small definition and the relationship. And then we are going to be talking about drift velocity of electrons. Under this topic, we have two subunits, that is relationship of drift velocity in terms of relaxation time. And the second one is the relationship of drift velocity with the current. So I have written down the timings of all of these three topics. If you want to specifically look at one, you can skip to that. Okay, so now let's start with current density. So the word density always stands for the total unit you're looking for divided by volume or length or area. Now we're looking at current density, which is called J. It is denoted by the letter J. And it is the amount of current passing through a unit cross-sectional area. If you're talking about a wire and you have, let's say, 5 amperes of current flowing through it, given the cross-sectional area is A, the current density is going to be 5 divided by that cross-sectional area. So that is current density. And as you can see, you can directly derive its units. I is in amperes and area is in meter square. So when you take it in the inverse, it becomes ampere meter inverse. This A is not area, this is the units. Unit. Ampere per meter square. So this is about current density. I'll write down the definition, you can copy it down. Okay, so here we have the definition of current density. It is the amount of current flowing through unit area. It's known as the current density. Okay, so now we are done with the first part. Let's go to the second topic, which is the drift velocity of electrons. Okay, so firstly, what is the drift velocity of electrons? If we talk about the average velocity of electrons inside a conductor, let's say this is the conductor. You know there are so many electrons over here. Each of these speck is an electron. All these electrons have random motion inside the conductor. That is, one could be in this direction, one in this direction, one over here, one over here. All of these have random motions, random directions of velocity. So when you average them up, when you sum them up after resolving the components, the average velocity of electrons is equal to 0. When you average them out, the electron's velocity is equal to 0 in the normal condition. But when you apply an external electric field, the purpose of this electric field is to orient the electrons towards any one direction. So let's say you are applying the electric field in this way. The external electric field is in this direction, left to right. And as we already discussed, the left side of the electric field is positively charged and the right side is negatively charged. That means electrons over here, being all negatively charged particles, would want to go towards the positive side. So all their velocities get shifted towards the left. So all these particles' velocities, which were previously in random directions, now are going to get focused in the left direction. So now there exists a velocity, and this velocity is called drift velocity. Drift velocity. This is because you're forcing them to drift towards one direction with the help of a field. So drift velocity is denoted by V with a subscript D. So this is about drift velocity. I'll write down the definition and then we can go to the derivation. So this is the definition. The average velocity of electrons after being exposed to an external field is known as drift velocity, and you must remember that it should be an external field, or else the electrons will just cancel out on their velocities. So now let's look at the derivation. So before going to the derivation, there's one more term we need to know, which is known as relaxation time. So let's see what is relaxation time as well. So now we are talking about relaxation time denoted by the symbol called tau. It's in this way. This is tau. Okay, so what is tau? The amount of time between two successive collisions of an electron is denoted by tau and is called the relaxation time. Okay, so the average time interval between two successive collisions of electrons is known as relaxation time. And why is this quantity important is because let's say you have an electron and an electron which are like almost to collide. You have an electron which is collided with another electron, and this is the first collision. So after this collision, this electron is going to have some energy, and this is now going to collide with another electron. So this is first electron, this is the second electron, this is still the second electron, and this now collides with another electron, 3. This time interval between two collisions, this is first collision, this is second collision. The time interval between these two collisions is known as tau. And this is basically the time that you're giving the electron to regain the velocity after this collision. Because after the collision with this electron, E is going to have zero velocity or very less, because it has transferred its kinetic energy completely. All subatomic collisions are perfectly almost elastic. So that's the condition here. So this electron is going to have zero velocity, but after some time it is going to regain the velocity due to the presence of external field. So, okay, wait once again. This electron collides and this is now going to have zero, but it is the same first electron which is going to collide with the third. So it needs some energy. This time interval from 1 is known as tau. The amount of time it takes for this electron to start from zero velocity and come back to its original drift velocity. That is the other alternative definition of tau. So now let's go to the derivation. We have both the terms we require. So to derive drift velocity of electrons, first we are going to, this is all we are doing with the basis of the laws of equations of motion. So we have the normal equations that V is equal to U plus AT. This is basically entirely the equation we are going to use. But here there are some quantities we don't know. First of all, we are going to assume this condition as soon as an electron collides with another one. So now after collision, the initial velocity is going to be 0, because you have an electron colliding with another electron. This is the electron we care about. This is the one we are studying with. So this electron collides with this. Immediately after collision, this is going to have velocity equal to 0. And this is the instant we are starting our observation. That means U, which is after collision, equals 0. It has to regain from 0 till its drift velocity by accelerating with the help of the external field. So U is going to be 0. So now we are going to modify this equation, and V can be written as Vd, which is the drift velocity. So drift velocity equals, this is 0, acceleration times the time. This is what we discussed. Time is tau. The relaxation time is equal to the amount of time it takes for that velocity of drift velocity to regain from 0 initial velocity. So now the only term left is acceleration. How do we find acceleration? Using F is equal to ma. So we have that the force equals m times a. But we have another equation of force, which is QE, from the equation electric field equals force divided by charge. From this we have an equation for force, that the charges that the electron experiences due to the field, which is E times Q. So I'm going to replace F as E times Q equals ma. Since it's an electron over here, the Q is going to be replaced by minus small e. Minus e. This E represents the charge of an electron, a negative sign because electrons are negatively charged. So we have this. And now we know what's acceleration from this equation. acceleration equal to minus E by m. This is the final answer. This is the final result of acceleration. Now we have to substitute this over here and our answer is ready. So acceleration equals E by m. So drift velocity Vd equals minus E tau by m. This is the expression for drift velocity in terms of relaxation time tau. So if you want, you can avoid this magnitude because we're talking. If you want to know the speed, you can avoid the magnitude. I mean the symbol, and you can write it as the magnitude of drift velocity equal to E tau by m. So this is the expression for drift velocity as a relationship with tau. Now let's look at the drift velocity in terms of current I. So I'll erase this off. So here we need a diagram, and the diagram can be the most simple one we can draw is a cylinder, a wire, conductor as a wire. So let's say this is our conductor material of entire length L and cross-sectional area capital A. So now we are going to consider a portion of this region, not the entire length but a small portion of this region which has a distance equal to Vd. I know Vd is a velocity, but you're going to take that distance as the velocity because that basically implies that the electrons will be able to travel from here to here in a unit time. Distance equals velocity into time. So when you take the distance equal to the velocity itself, it basically means that it only takes 1 unit second. If you have taken the distance in meters and velocity in meter per second, it only takes 1 second for that particle to travel that much distance. So that is what our observation is here. We need the experiment to be held only for 1 second at an instant. So we are assuming the distance to be equal to the drift velocity of the electrons. So what's the purpose of doing this? Now, the velocity of the particles equals the distance equals Vd. So now we need to find current. So when you start with the formula for current, I equals Q times T. So this comes from the formula that Q is equal to I by T. So now we have I is equal to Q times T. And now we conducted the experiment only for 1 second. Okay, so now we are going to look at, let's see how to start the derivation. We are looking for current I. So let's start with an expression of I we know. So I is equal to Q by T. We know this very well. And the time is basically 1 second. And that's the point of assuming Vd equals V. Time is 1 second. So it just means current is equal to the total amount of charges which are present in this region. If you figure out how much charges are there in this region, it means you have already figured out the current in that region for this case. So what is the total amount of charges in that region? And we know another formula for charge which was in grade 10. Q is equal to N times E. Is the number of times how many electrons are present over there. Sorry, it's the number of electrons times the charge of 1 electron present over there. Charge of 1 electron is a constant. So we only need to know how many electrons are present over there. So I'll just replace this Q with N times E. N. So now we need to know how much electrons are present in that region. So now how do we find out how much electrons are present over here totally? Here we need to introduce a term known as electron density. Electron density is denoted by N. That's why we will change this to capital N. Capital N stands for the total number of electrons. But small n is equal to electron density. Now again, this is a density term, but this time it indicates per unit volume. That means electron, so now we can make a relationship of N. So N is equal to capital N times divided by volume, where capital N is the total number of electrons. So how much electrons is present totally but in this region? So that means we need the volume of this region. So what is the volume of this region? Cross-sectional area is A, height is VD, and you know the volume of any symmetrical figure is the base area times the height. So base area is A times the height, is A times drift velocity. That is the volume. So volume multiplied with charge density, electron density should give us the total electron present over there. So N is replaced by electron density times the volume into E, and electron density is a constant and volume is A times VD into E. So this is the total amount of current in the region. I equals NAVDE. This is the expression we are looking for. The only catch over here is to find out the total number of electrons, and for that we are assuming a quantity called electron density, which is total amount of electrons divided by volume. So when you multiply electron density with volume, you get the amount of electrons present in that volume. So electron density times the volume you are looking for is A into VD into the charge is the total current. So now we found the relationship of VD with I. So after this we'll be able to modify the current density. So for now this is what we are learning today. So in the next video we'll talk about how the current density can be modified in terms of resistivity, conductivity and all that. So yeah, thank you for watching and see you in the next video.